So our graph, we need the gradient to work out the spring constant. Okay, so our gradient is our spring constant. Rise over run. So our rise, 40 newtons. Is that right? 20 newtons, sorry. 40 millimeters. Right? What am I doing? Rise 40. I'm looking at the whole linear bit. Rise is 40. What's run? 20 millimeters. Now, remember, millimeters. Need to put it into meters. Okay, so 40 over 0.02, that's about 2,000, I think. 2,000? Yeah. All right. So our spring constant is 2,000 newtons per meter. Okay, so part B. Calculate the strain potential energy that the wire can store before permanent deformation begins. We need to look at the area under our graph now. And the nice bit is the area before permanent deformation. Yes? Oh, I did. Hang on. 20 millimeters. Are you sure? It's correct? Okay. Ivan, if you come for the king, you better not miss, my friend. Okay. Sorry. Couldn't resist. It's still all the adrenaline from the basketball match. Okay. So, I am recording that, yeah. So your parents will hear me threaten you. That's great. Okay. So for this, we need our area under the graph. Okay. Now, under our graph, you'll notice that it's a nice linear part, and so it's a perfect triangle. So it's easy to work out the area of a triangle.
Did you say area under the graph?
Yep. Sorry?
Did you say before the area under the graph is work around here?
Yes.
Is that the same as the...
Yeah, because energy is the work done.
Sorry.
That's okay. All right, so the area under our graph, half times base times height. Now I did it up here before. 1/2 times our base is 0.02 times 40. That's going to be a very small number, 0.4. Is that right? Someone with a calculator want to check that? That's right. That's times 40, sorry. A little dot in there. Okay. So there's the work done before permanent deformation begins. Now we need to work out the work done to break the wire. So, again, this is a case where you're going to need to go under the graph, work out what each square is worth, and then work out how many squares are covered. Okay, so you've got the first part. You know the linear part is 0.4. So, see what you got there? So each square is worth 10 newtons and 5 millimeters. Okay, so each square is worth 10 newtons times 5 millimeters. So 0.05 joules. So count them up. How many squares have we got? I don't have my sheet in front of me. Someone's going to have to tell me.
21.
You've got 21? Do I have an advance on 21? Anyone agree? Anyone disagree? How many squares are under the graph?
Just only this part.
No, the whole part.
The whole part.
Yep, up until the breaking point, because we want to know how much to break it.
Can't you see that from the previous question though?
You can use the first part from the previous question, but then you have to estimate the rest. So we've already got this bit from the previous question, so just count up the rest.
Oh, yeah.
Well, you'd need to count both, but we can add it to what's under the linear part. We've got 32? 32-ish? No, because this breaks down once you get past the elastic region. This doesn't work once you get past the
So that only works there.
It only works with the linear part.
Oh, okay.
Once you get beyond the linear part, it doesn't work anymore. I'm hearing 33, Michael? 33? Alright, I'm happy with 33. So, a number of squares. Alright, so our work done, or our elastic potential energy. Let's go. Oh no, hang on, we want work done. It's 33 multiplied by 0.05. There's red dots everywhere. And what's that equal to? 1.65. So it takes 1.65 joules of energy to break our wire. Okay, so it takes 0.4 joules that can get it to its deformity. Okay, once you add 0.4, it'll be permanently deformed. If you keep adding energy to it, you get up to 1.65, you'll break it.